Okay, 3, 2, 1. Hello, I'm Susan Nash, AAPG, and I am just so thrilled to let you know that today's agenda represents an amazing breakthrough for us as a society. And I'm really, really thrilled because we are having the opportunity to debut work from the USGS that has to do with water quality, but specifically looking at groundwater threats to principal and secondary aquifers from orphan wells. And I mean, that's a complex issue. We were chatting a little bit before the beforehand about some of the things that we'll be talking about, but it's just really, really an important question, and it ties directly to what AAPG's mission is, which is promoting the science, but also in our division of environmental geoscience, it really has to do with making sure that we understand the environment and the impact of oil and gas and energy, subsurface energy operations. So it's just really exciting. So our presenters today are all with the USGS: Josh Woda, Carl Hazy, and Nick Janutzis. And I just want to say also that they have been involved in the APG's Orphan Well conferences, and we plan to have more in the future. So we've had 3 so far, and they've been wonderful. And also we've had numerous webinars that have dealt with that topic, but this is the first time we've really directly addressed the issue of aquifers. And before we get started, I just want to say thank you to our attendees. And I want to remind you that you will be getting an email with a link to the recording so you can watch it on demand, and you can also share it. And also, I'd like to say that if you have any questions, please put them the in the Q&A, not chat, but Q&A. That will help us determine which questions to answer. And some of you sent questions ahead of time too, which is great. And then finally, I just want to say thank you to our Division of Environmental Geoscientists. Thank you to our President, Matthias Imhoff. And also thank you to our President-elect, Dan Arthur. So anyway, with that, I'd like to invite Josh to share a screen, and thank you.
Great. Is my screen showing?
It is, and it looks great.
Okay, awesome. Thanks so much. Thank you, Susan, for the introduction. So again, we're really excited that you guys are here today. We've got a nice packed agenda from our end on a couple of different talks that we hope you guys will find interesting, and excited to share and hear your thoughts and comments for all of this. So I'll be leading the way with the talk, about our recent publication about orphan wells and groundwater threats to principal and secondary aquifers of the U.S. Carl Hazy is going to follow me up with an overview of water quality near orphan wells. He's going to showcase a little bit of our story map that we put out recently. And then Nick Janutis is going to carry down the anchor for us, and he's going to showcase a number of different products that we've been working together as the USGS Orphan Well team. So with that, I'll kind of jump right into the talk. All right, so this was some work that we accomplished last year. Put a big effort into thinking about these questions, and I'm going to go into just a little bit of background for you all before we kind of outline how we're going to go through this talk. So I think for many of you, this will not be new information. The first commercial oil well in the U.S. was drilled, in the roughly the middle of the 1850s. It's the long legacy of drilling in the country, as many of us well know. Many of these wells, in their initial plugging and abandonment, were plugged in and cemented in a way that I think, many of us understand would probably be insufficient to today's standards, which is an important consideration for groundwater. For our, just to put some definitions out there, an orphan well, which is really the major group of wells that we're thinking about, is defined as an unplugged, non-producing oil and gas well that has no responsible owner or party to remediate the site. Oftentimes this burden is left on government agencies, occasionally landowners and non-governmental organizations as well. So there's kind of just less people that are directly responsible for these. A bit more background. We know there's over 117,000 documented orphan wells. We know that's an over number because we know there's also many undocumented orphan wells, which is an important consideration. Orphan wells pose risks to both air and water resources. Really, most of this initial work that's been done has really focused on, air emissions from these wells. Less has been done mostly for thinking about this in terms of groundwater resources. Orphan wells are unique to other types of oil and gas activity, really due to the large number of unknowns surrounding these, particularly as it relates to well construction, well integrity. And as I mentioned before, we don't even always know where all of these wells are. Generally speaking, this and a number of other reasons make it extremely difficult to link groundwater contamination to orphan wells. So how I'm going to go through this talk, I think for some of you, this may be some background. For many of you, it may be a little bit new. But so for the first part, I'm going to just talk about just kind of general threats to groundwater activity from oil and gas activity in general, with this understanding, right, that many of the lessons that we've learned from kind of around this space are directly applicable to orphan wells. The second part, I'll go through our recently published study, which I think came out officially maybe a few weeks ago. But really the major question we'll be answering for that is which aquifer systems across the country may be most vulnerable to contamination from orphan oil and gas well activity. So let's jump into some of this background. I think there's been a long history and a long understanding that, oil and gas wells can provide connection to freshwater aquifers from other formations. This is a study, from the early 1980s, where they were thinking just about this in Pennsylvania, these potential pathways, these potential contaminants. Two typical, and I say typical because of course there's more, but two typical contaminant classes from oil and gas wells that we think about are hydrocarbons and, these oil and gas constituents and brines, which, that saltier fluid that's often found at deeper depths. In terms of hydrocarbons, hydrocarbons can either be gaseous or in the dissolve phase. You can see we've got right here, this is a video of an orphan well in Pennsylvania. We're bubbling some hydrocarbons in this case. We detected high methane here, but for many of us in this space, this is not an uncommon sight. In addition to, gas phase hydrocarbons, we can also have, constituents dissolved in water. In this case, this water is another site in Pennsylvania. Very high dissolved methane in this water. As it comes up to the surface, that methane is quickly dissolving out of solution, which is why you're seeing this milky color. Methane doesn't like to be dissolved in water typically at surface atmospheric pressure, so it comes out pretty rapidly. In both forms, methane can present an explosion hazard at high enough concentrations, and especially in confined spaces, which is a concern. In addition, when you have really high concentrations of different hydrocarbons, a particularly strong leakage, you can actually also kill vegetation. This is from another paper in Pennsylvania where, we observed some dead vegetation around some areas where there was the large leakages coming out of a farm field. And then finally, we often think about these direct kind of contaminants that are coming from oil and gas, but hydrocarbons can also cause secondary concerns in aquifers. In particular, hydrocarbons can feed a number of different bacteria. These bacteria almost go into a feeding frenzy in some cases when there's a lot of hydrocarbons around. And this can result in metal mobilization. You can see this is kind of an example of one of these bacterial mats that can lead to, mobilization of metals such as iron, arsenic, and manganese. Can also create hydrogen sulfide, which is, a lot of us are used to that and concerned about that on some of these sites. That rotten egg smell in particular. So it's actually often a byproduct of, these bacteria going to town on some of these hydrocarbons. So we can think about these in the surface, but really when we think about aquifers, we think about what's going on below our feet. So this is a diagram of, one of these plumes from a potentially leaking well. As it kind of expands over time, where you can have potentially degradation of the aquifer from the secondary effects too, where you might see metal mobilization and also sulfate reduction to hydrogen sulfide. In addition, we often think about brines, another potential contaminant. We know again that these improperly sealed wells can provide this conduit to these typically deeper formations that are oftentimes much saltier. This is a picture out of Texas. We know there's a lot going on down there with some produced water that's being injected into depleted oil and gas reservoirs that's making its way in some cases out of orphan wells, in some cases it may be even out of plugged wells. And what you're seeing here is not, in fact, snow, it's a salt crust. Brines they can also include other species. They can include higher concentrations of radiogenic species and metals. So we're not just always thinking about salts. And this is a study from West Point, Kentucky, where they were looking at some migration of high connectivity brines moving from some abandoned wells towards some public supply water wells. Brines can also be corrosive. I'm not going to touch on this too much, but these are some pictures from our colleague Carl Hase. I'm sure that many of you have seen similar sites that are working on many of these areas. We know that this infrastructure, especially over time, can break down, and brines can be one contributor to this. And this is actually an area of pretty active research for us right now, thinking about this corrosivity. So I don't want to spoil too much of the fun there. And finally, to kind of wrap up this section, just kind of thinking about how we go about one of these studies. It's very challenging. And I'll be the first to admit when we think about these kind of questions, tying any kind of leakage from any oil and gas activity is really difficult. We know that hydrocarbons and brines occur naturally in groundwater, which makes it challenging to distinguish that directly. What's potentially coming from a contamination event and what's already there. So, we often call this an environmental forensic study on our end to kind of try to parcel that out. And we'll typically try to use multiple lines of evidence to answer this question. If we have pre-drill or baseline data, this is kind of the gold standard. If you knew what water looked like before, I can tell you oftentimes it doesn't exist, which makes the job particularly difficult. So we might then have to use other tools. Isotopes are a common theme where people may look at carbon and hydrogen, especially in methane, to identify, where is that gas coming from? Is it from a biogenic source? Is it from a thermogenic, deeper source? There might be some brine tracing to go on, which formation is the brine coming from, along with a lot of other additional information that might be useful. So with that, kind of just to wrap it up, we talked about a number of these different contaminants, these, potentially contaminant pathways and how we think about this. I just want to reiterate that a lot of these things that we've learned from the space are directly applicable to orphan wells. So now I'm going to kind of dive into our recent publication, a geospatial analysis of water quality threats from orphan wells and principal and secondary aquifers across the United States. So kind of to go towards these goals and questions of this work, we really wanted to think about the orphan wells in the context of, the principal and secondary aquifer systems of the country. And I'll go into what those are for you guys. So in the top right-hand side, we've got a map of the principal aquifer systems across the country. This mass of purple, they're actually dots, but in some cases, there's so many of them that they're all grouped together, are the orphan wells. And this right here are the principal aquifer systems. These are the aquifer systems in the country where most of the groundwater extraction comes from. Greater than 90% of groundwater extraction in the country comes from these principal aquifer systems. That's not to say that the areas in between are not important. They were recently characterized as the secondary aquifer systems, and we know there's still plenty of users within these. So we decided to think about both of these in terms of orphan wells. Generally speaking, about half of orphan wells fall within a principal aquifer system. And really the major question that drove our research was which aquifer systems may be more prone to water contamination from orphan wells. We thought about this from a water withdrawal standpoint, which of these systems have a lot of water withdrawal where there may be many orphan wells, and then where is leakage more likely, based on a number of different factors about the aquifers themselves and also about the orphan wells. So how did we go about this? Ultimately, this was a geospatial exercise that we did with a little bit more added on. We compiled and spatially joined the orphan well database, the principal and secondary aquifer systems that we just showed before, and then 8 different factors all into a GIS database. For these factors, as I'll say throughout, we know that there can be many more factors, but we focused on ones that had a lot of good evidence in the literature and also had really nice data sets that we could look at nationally. Pretty simply, and this is the low-hanging fruit, is we looked at the number and density of orphan wells within these systems. We looked at a number of factors related to well integrity and contaminant transport. And then we looked at a number of factors related to kind of the user groups and the people that are maybe within these areas where there's orphan wells. We assessed these factors individually, and I'll go through a number of these factors with you guys and kind of what we found. We also looked at where there might be the coexistence of multiple factors. So where do these start to kind of mesh together? Ultimately, we kind of classify these in different groups and combinations. So first off, we looked at the number and density of orphan wells. I'm going to showcase a lot of maps that look like these. And generally speaking, the lighter the color, the less of something, the darker the color, the more of something. So in this case, for the number of orphan wells, these darker color areas represent regions where there's more orphan wells. So the Northeast really stands out, which is not surprising given, kind of the birthplace of a lot of the drilling in the United States. Midwest also standing out as well. We also thought about the density of orphan wells. So now we're thinking about the number of orphan wells in relation to aquifer size. See the Northeast scale stands out. We see California start to pop with some of these smaller aquifer systems. In the Oklahoma area too, the Anabamusa aquifer, which is this little kind of diagonal, I'd say almost like a lightning bolt, was an area that actually had the highest orphan well density for any principal aquifer system. And I know there was a question leading into this regarding the Osage Nation, and the Osage Nation is within this aquifer system. So something, a lot of orphan wells in that region for sure. In addition, we thought about well age. We didn't have a lot, one of these things that I mentioned is often missing from orphan wells is a lot of information about well construction and well integrity. So we looked at well age as a proxy for this, with the general idea that the older these wells are, potentially the more well integrity concerns there may be. And we know there's other metrics for this, but this is one that we were able to use for this nationwide study. Older wells, again, no surprise that we're seeing a lot in the Northeast, a number again similar in the Midwest, and also on the West Coast as well for a lot of these older age dates. In addition, coal was another important factor we thought about. Coal is, you can see on the map, is we've got these hashed areas represent the large coal fields that are mapped across the United States. Coal interaction with oil and gas wells pose an array of possibilities. You may have methane that's within these coal seams themselves, but also when there is underground coal mining in particular, you may see land subsidence. Acid mine drainage is a common thing. And if you're unfamiliar with acid mine drainage, this is a process by which, when you introduce typically these oxygenated waters into these seams that maybe did not have oxygen before, they can result in some geochemical reactions that produce typically low pH waters, very high TDS. There might be very high metals. This is a site in Pennsylvania of an outflow from an underground coal mine. And you can see this kind of water interacting with orphan wells might not be ideal. Kind of with that in mind, we thought about corrosivity of these aquifer systems in terms of what may break down well integrity over time. You can see the East Coast in particular typically has more corrosive conditions. We also thought about aquifer types, aquifers that maybe have fracture flow or karstic void flow, maybe being more susceptible to potentially transport contaminants in the event of leakage. And then finally, for these individual factors, we thought about the land use. Where are orphan wells in relation to different land use types? We thought about a number of them, but two that we really kind of honed in on are where are orphan wells in relation to open water and wetlands, thinking that these might be kind of risk-prone communities in particular, if orphan wells are located within these areas. Also developed land, are orphan wells located in direct proximity to infrastructure, to homes, as being a little bit more of a concern as well. And then, of course, we thought about, how much groundwater withdrawal is coming out of these systems. And you can see it's maybe not surprising. California really stands out with a lot of groundwater withdrawal in relation to these, where there might be orphan wells, also some near the Gulf Coast. So we thought about these factors individually. The next thing we really wanted to think about was, which of these aquifer systems might have multiple of these different factors kind of occurring simultaneously. It's going to be, a plot to look at, but we'll get through this. We're looking here at, we call this, we're looking at now orphan wells. Did I stop? A second. Technical difficulty, but okay. So we're looking at orphan wells in relation to groundwater withdrawals. So on the y-axis, we're looking at the potential withdrawal impacts. So we're looking at orphan wells in relation to groundwater withdrawals. So really how we like to think about this is, these kind of aquifer systems have more orphan wells in relation to a lot of pumping. So which of these aquifers might have a lot of water withdrawals that could potentially be impacted by orphan wells. On the x-axis, we're looking at how we like to think about this is orphan wells as it relates to just the sheer number of groundwater withdrawals and the sheer number of orphan wells that are kind of within these systems. So you can see something like the Atabamusa aquifer, which has a lot of orphan wells in relation to the groundwater pumping stands out. And really how we kind of look at this is, really these wells on the upper right-hand, these aquifers on the upper right-hand side, the Pennsylvania aquifer and the Mississippian aquifer, really stand out that they have a large amount of groundwater withdrawal and a large amount of orphan wells to think about this factor. In addition, we wanted to think about, the susceptibility of these aquifers to, potential contamination. And the way we wanted to think about this was in terms of well integrity and potential for contaminant transport. So for this, we thought about, we're looking at all of our aquifer systems now, our principal and our secondary aquifer system. And we thought about 4 different factors to kind of think about this. We thought about where there might be high corrosivity groundwater, which of these orphan wells are in aquifer systems that overlie a coal bed, orphan wells that might be older in age, and we thought about 2 different date cutoffs for that, and then aquifer systems where preferential flow might be more likely. None of these aquifer systems had all of these at the same time, but we can see that there are a number of aquifer systems that had a large number of these factors simultaneously, which has some implications for thinking about the potential threat to these systems. And then finally, kind of to wrap this all together, we really wanted to think about, which of these aquifer systems, kind of have similar characteristics together, where they might have similar withdrawal metrics, similar well integrity concerns. And so what we did was we created a hierarchical cluster analysis. This is a kind of a fancy word for grouping things together based on just that, the susceptibility factors and this orphan well integrity metric, which is that groundwater withdrawal metric. You can see a number of different groups stand out. The first being this kind of red group, which is actually just the Pennsylvania aquifer alone, kind of stands out because it has all of these factors together, a number of these susceptibility factors and a pretty high groundwater withdrawal. These blue areas stand out. You can see California really stands out. Mississippi River Valley alluvial aquifer system stands out. These kind of stand out because of the large amount of groundwater withdrawal that occurs within these systems, which is an interesting consideration around orphan wells. The yellow kind of represents middle of the road, kind of a middle number of these susceptibility factors and these groundwater withdrawal metrics. The green, we're kind of on the lower end for both of these. Not to say that there aren't other factors that are relevant, but in this study, this is how this came out. And then the light blue are interesting in that they stood out just kind of sheerly based on just the very old age of the orphan wells within these systems. So just a kind of a nice way of grouping these and kind of thinking about aquifers that might have similar characteristics. So to kind of wrap this all up, we looked at several factors, many of which could influence groundwater contamination from orphan wells, and we tied them both to the principal and secondary aquifer systems. Kind of a big kind of metric that stood out for us is that about 54% of the studied orphan wells are within aquifer systems that supply 94% of the nation's groundwater use. So, really just kind of driving home the importance of thinking about these issues. We identified a number of groups of different aquifers with kind of similar characteristics. Some regions really stood out to us in that regard. The Appalachian Basin, I think, stood out from a number of our metrics, the Gulf Coast and the California aquifers in particular. But that's not to say that this is not something to think about all over. And really just, I want to reiterate that we designed this study, for a user to kind of get a sense of what they're dealing with and maybe their area of interest. So, we have aquifers mapped across the entire continental US with these data sets. We invite you to come take a look at, your aquifers, get a sense of what factors there might be there, how many orphan wells are present within it, and really just kind of start thinking and driving home these issues and really to provide just, some resources for you all that might be useful. So with that, I am going to wrap things up, and I think I will be passing this over now to my colleague, Carl Hase.
Hey, thanks, Josh. So let me, are we live with my screen?
Yes, you need to do the presentation
Okay.
mode, please. Yeah,
Look at that. Live from the beginning.
here we go.
All right. So I'm Carl Haase. I'm a research chemist at USGS. I work with Josh and Nick. And today I'm going to be giving you an overview of a story map that we made to help you use water quality data that the USGS has collected to help you understand the water quality near orphan wells. And I'm presenting this as a conjunction of a project that I did with Chris Skinner and Nick Januchis. So in 2024, we released a data set of groundwater quality measurements near orphan wells. And that data set contained measurements that we pulled from 8,585 water wells across the United States that are inside the USGS National Water Information System. And those water wells were all within 1 mile of about 19,708 orphan wells that are that we got the locations from the USGS documented orphan well data set. So this combined data set has measurements of water quality parameters like pH, temperature, total dissolved solids, dissolved hydrocarbons, some isotope data, some brine data, things that we thought would be useful for understanding the water quality near orphan wells, and that could be helpful for people trying to understand if there was a legacy of water quality impairment, or what the just general water quality is near orphan wells, or how that water quality could actually impact the orphan wells. So we released that in early 2024, but one of the challenges is that this is a fairly large data set. It requires ARC or some other kind of geospatial package to view. And that really isn't making our data accessible to other users and making it useful for decision making. So we looked at the data and we started talking with people and listening to the questions they had, and there's like common maps, and we created a story map, which is something that you can use in your web browser to look at common water quality parameters that could be really useful for making decisions for plugging and prioritizing wells for plugging. So while I'm going to keep talking from PowerPoint slides so that I don't wander off track, and frankly, my computer is not all that fast, I encourage you to go look at the story map now and kind of work through using the story map as I'm talking about using it. So I posted a link into the webinar chat. If you want, you can take a picture with your phone, and I'll walk through the story map. So when we made the story map, we targeted 3 general groups of users. We targeted people in industry. We heard that people wanted to know what kind of water quality challenges exist near wells that are being plugged. We heard from policymakers that they wanted to be able to use water quality data to prioritize plugging efforts. And we heard from researchers that they want to know, where has the USGS already collected water quality samples that they could use to build on their orphan well related research projects? So the story map has several intended use cases, things like safety, well and well plug integrity, and plug design. The water quality parameters that we pulled out to answer those questions are specific conductance, which is a proxy for the total dissolved solids in the water. We pulled out chloride, dissolved calcium, sulfate, corrosivity, and dissolved methane. And you can see that at the top bar of the story map. So you can click between those individual parameters. So one example question that we thought someone might ask is there groundwater chemistry that could cause sulfate attack on the cement in the orphan well or in the abandoned well plug? And to answer that question, when we put together the sulfate section of the story map, we chose concentration gradients in the legend that roughly correspond to the American Concrete Institute recommendations and the DIN 430 recommendations for sulfate attack of concrete. So, for example, if we go look in Western Kentucky, we can see that there's an array of sulfate concentrations in groundwater, and that there's some areas near orphan wells that have elevated sulfate. And if you're plugging a well, you might want to change the formulation of the concrete or cement that you're using to plug the well to be more resilient to this high sulfate groundwater. Another example question is, could the groundwater near a well that I'm going to be working with be corrosive to the well materials or the plug materials that we're using to plug the well? Corrosion processes can affect all materials in a well and well plugs. That can attack both metal and cement. We used an index called the Langolier Saturation Index. It's a very general corrosivity index. It's based off the saturation of calcium carbonate in water. The more negative the LSI index is, generally the more corrosive the water is. And that index roughly corresponds to both corrosivity to metals and cement. So if we go to Western Oklahoma, we can see that as you move across the state, as you east to west, there is a horizon of corrosive groundwater that transitions into a horizon of less corrosive groundwater. And this could be useful for planning for the well condition before you go in for plugging activities, or for considering what materials you want to place inside the wellbore that you're plugging. The third example question I have is, what are the methane levels in groundwater near the well that I'm plugging? Should I expect there to be high microbial methane? And maybe there's a concern about water quality near that well. Like, is there existing data that we can use to compare our samples to? So I chose the California coastal basin as my example. And that's not the right word for what that is, but nonetheless, Southern California. And that really stands out because, like, right at the coast, there's lots of high concentrations of methane in groundwater near the orphan wells. But as you move inland, the concentrations of methane quickly drop. So we're really proud that you can go and see what data we have near documented orphan wells and use that to help understand what the water quality parameters are near your projects. So with that, that wraps up my short demo of the story map. Nick's going to say this: I'm really interested in getting feedback on this product and to hear what other ways that we can make our data and science available to you.
Thank you, Carl. Okay. All right. So I'd like to thank Josh and Carl for leading off. And I'm just going to talk for a few minutes about all the science that we're doing at the USGS in support of orphan well plugging. Over the past couple of years, we've created multiple publications and data sets that contain things like well locations, well ages, groundwater quality, and produced water's geochemistry. That hopefully is useful when you guys go out and plug wells. Josh talked today about, the threats that orphan wells pose to groundwater quality across the nation. And so no matter where you are, where you live, you can look at what those threats are locally, see how they compare to other areas of the country. Carl just gave us a demo about our groundwater quality near orphan wells interactive story map. And this is a tool designed for people out in the field, plugging wells, putting cement in the ground to look at, what's happening in their area with groundwater quality, corrosivity, and other factors. And so the goal of the USGS Orphan Wells Project is to create these types of tools for you to help you in your efforts to plug orphan wells, to understand more about the nature of orphan wells, whether that's leaking contaminants, plugging locations, finding new orphan wells, etc. So right now we're working on doing continuing research. We're going to continue to look at groundwater quality. Is a very hot topic right now. We're going to continue to look across the country and put out more studies. We're also getting out in the field and looking at wells and measuring leaks in places like Montana, Oklahoma, Colorado, Ohio, and Pennsylvania. And then we're going to have a paper coming out soon on wellbore deterioration, looking at corrosivity in groundwater and the impacts that that can have on orphan wells. And so we are always interested in receiving feedback from you. You're the ones who are doing the work. You're out there actually plugging the wells, seeing things in the field. And we get a lot of really good ideas from the feedback that we get from talking to people like yourselves. So we appreciate you taking an interest in our work, being here, and providing that feedback. And we're also looking for opportunities to collaborate. We have a handful of partners in whether it's states or nonprofits or other government agencies that we get out, that take us out into the field with them and we work with them. Here is a list of all of the products that we currently have available. If you just Google USGS Orphan Wells, you'll find our website, which has all these publications. But we do have the map of 117,000 orphan wells. What Carl just talked about here is the groundwater quality near orphan wells story map. We do have a database from our produced waters group that looks at the geochemical information from produced waters across the nation. So if you're designing well plugs, you know, it's very helpful to know the environment that those plugs are going to be sitting in. We also have a paper looking at the sources of methane emissions and then an analysis of all the orphan well data that we have for 117. So this is our personal contact information. Feel free to reach out. Send all your really hard questions to Josh and Carl and send easy ones to me. But we're always looking for feedback and a chance to collaborate. And with that, I think we'll go into our question and answer portion of the talk. And I guess the last thing I'd like to say is I just really like to thank AAPG for the opportunity to present our research today and all of you for coming and taking an interest in the work that we're doing. So thank you.
Thanks, Nick. Really great. And again, I really want to thank all three for allowing us to share and debut this really important study. So we have a number of questions, and I'll start with the ones that have been voted to the top. So anyway, the first one is Lawrence Walker. He said, this is a history matching question. Is it possible that aquifers dump fresh floodwaters into deeper drawn down oil and gas reservoirs via infinite acting permeability pathways? Do we ever test for this? Could this be a large enough part of the drop in FW levels we are seeing in the mid-continent that we are ignoring? That's a complex question.
I guess I can start. I don't necessarily know if this has been studied in depth, but it is definitely an important consideration to think about, you know, potentially draining aquifers in relation to boreholes of any kind. You know, if there were impermeable kind of confining units in between two areas, when you connect them, there's always a potential for something to happen. But I don't know if this has been actively studied in any capacity. Carl, I don't know if you know of anything.
So I know that the California Water Science Center has spent a lot of time trying to understand the legacy of drilling in the LA Basin. And one of the things that they think is happening in some parts of the aquifer is that they think that there is some cascading of the aquifer into the legacy wellbores. They don't quantify the volume of water loss. They think that they can detect a cone of depression, but I don't know how big that is or what that implies.
Well, that's interesting. And it seems to me that it all kind of comes back to the issue of the condition of the hole and borehole integrity, et cetera. What's actually going on there. And so this is kind of leads to our second question. Did you look at impact of time in 5 years, 10 years, 15 years?
So, you know, just to be clear, that this study was not necessarily a look at, you know, individual cases or, you know, impacts directly. We were kind of taking a more holistic, larger kind of view of, orphan wells and, potential threats to these different aquifer systems. We weren't necessarily looking at individual cases. So although I think this would be a fascinating kind of avenue to look at over time, and there are likely some cases where we could do this, this was not the focus of this research.
I kind of wonder what the question is really driving at too. Like, is it impact of 5 years after initial plugging, or is it 5 years after it's determined that it's an orphan well, or like, I mean, it would be interesting.
Oh, I think all of those questions would be interesting to answer.
Yeah, which kind of reminds me of some of the work that was done, like, in Wyoming in the Teapot Dome area, where like, they just all these test wells, just seeing what happens over time.
Yeah.
Okay, so let's go to the next question. Miguel Yilalis asks, thank you for your presentation. Is there any reason why the high density of orphan wells in the Marcellus area, in the Marcellus area, as compared to other areas, as in Texas?
I can answer that one. So I guess I'm not sure specifically what's happening in that area, but one of the things that we see is orphan wells tend to be divided into two categories. You kind of have your legacy drilling, because plugging standards started sometime around the 1950s, depending on the area. So older wells, 1800s, early 1900s, didn't have a lot of plugging standards in place. And so generally those wells are orphan today, but they're hard to detect. And they're some of the hardest wells to document and define. And then newer wells, kind of in the modern era, after plugging standards are in place, are usually the result of if a company is like declared bankruptcy. And there's a smaller amount of those number of wells, but we also know where they are. And so what I would suggest is going into the tool that Carl showed. You can go in and actually click on those wells in that area and see. Sometimes they have dates that they were drilled and kind of see what era they were in. And that'll kind of give you an indication of when they were drilled, who they were drilled by. Often API is contained in that data as well.
And also there might be some issues of classification. So for example, in Texas, you can file to have your well as a kind of like idle or temporarily abandoned, or almost like ad infinitum. So it's not orphan. And then it turns into orphan, like Nick was saying, when it's when there's bankruptcy or disappearance of the owner, whatever. So that complicates the issue, because how long has this been kind of like a de facto orphan well, for having been temporarily abandoned for way longer than other states allow? What happens? So it gets complicated. Okay, so we have a question that was voted way up. And so let's find, oops, I just lost it. Here we go. This is from Gary Randall, and it was upvoted. So do you use any tools that you can ascertain if there is wellbore integrity? Okay. Do you use any tools that help you ascertain if there are wellbore integrity issues below the surface? There are very sensitive acoustic tools available that have been proven to detect methane migrations outside of surface casing.
Yeah, I can give this a first go. So for our work, we have not been, doing this kind of analysis. And I think there probably are, maybe regulators and pluggers in the audience here that might have a better answer for this, or might be using specific tools. In the USGS, we do a number of, borehole geophysical investigations. And I agree that, acoustic televiewers, optical televiewers, maybe even something as simple as a caliper could be a useful instrument to kind of get a sense of what wellbore integrity might be like. But that's also, considering the fact that you might have an unobstructed borehole to be looking at, which, for some of these orphan wells, we often don't know what might be going on downhole. I know DOE is looking into non-invasive methods to consider wellbore integrity. And I think we actually have a proposal in now to do that kind of looking too, but I'm not sure what the state of all of that is. So yeah, I mean, it could be something that's, you know, maybe incorporated into how we think about these issues. But right now, it's, at least from our group, this is not an actively ongoing project.
Great. So here's a question for all of you. Are some of these data open and free to download?
Nick, do you want to say where people can find all this?
Yep. I just posted a link in the chat, and I'll type one in this answer here. So everything is available on our website. All USGS publications are free of charge to the public, and we try to make everything we can available for download on our website.
So Bert Vogler, who is our former president of DEG, who's located in California, has a question. Has the Trump administration's have the Trump administration's cuts affected your research? And if yes, how?
So right now we're facing a lot of uncertainty, and we've, last couple of months have adapted to a lot of changes. And we're still kind of waiting to see what the final impacts are. But so far, we've been able to continue doing our research. And at the USGS, we're very committed to orphan well science, and we're going to continue to do the work we can with whatever resources we're given.
That's good. Okay, so we have a question from Michael Dolan, and he refers to one of our visionary scholars and publishers in the past. In California, for example, Les Magoon and others conducted a comprehensive SEEP study. Do your teams consider integrating those types of studies as well?
Carl, are you familiar with that study?
I'm not. My thought is, my response is that we are eager to learn everything possible about the challenges at the orphan well groundwater nexus. With this specific project that Josh worked on, we needed to work with things that we could project on a national scale, but we are very eager to learn about how things we learn at the site, local, regional, basin scale can be expanded to a national scale understanding.
So yeah, Michael, I would say if you want to send that our way, we would definitely appreciate it.
I think this type of integration is so exciting, and the types of things we can do with analytics now, just to tease out relationships, is really potentially very fruitful. Okay, so Skylar White is in attendance. I want to thank him for attending. He's a rancher who has a ranch in Texas that has a number of orphan wells. Anyway, he said, thank you for looking at groundwater contamination as it relates to orphan wells. That is a larger concern versus methane releases. One thing to think about is the groundwater withdrawals in the middle and western United States. Although the rate and total groundwater withdrawals are smaller than in the eastern U.S., it's a larger issue due to the greater importance of groundwater to the populace and agricultural community versus the scarcity of supply.
Well, I actually think, some of the aquifers in the Midwest in particular, like in the Ogallala aquifer actually has, the largest groundwater withdrawal of any aquifer in the country. But thinking about the importance, I think we did in our paper think about, the user groups of who is withdrawing and using groundwater. I don't know that we necessarily, came up with a metric of importance to different people, because I think that was kind of just outside the scope of what we were doing. But I don't know, Carl, do you maybe have additional add-on for that?
My add-on, I think, would be that we are thinking about water stress as a variable for future projects. because you know that we weren't able to come up with a nice factor for this study in the time and resources available. But that point is well taken, that
And I
we are
think,
thinking about water stress.
and I think too, it raises, Carl going, it raises another question is, I think we thought about this groundwater withdrawal, on this aquifer scale. I think what we would love to do if we had the time and the resources would be to think about, a little bit, kind of to get at this question about, where are orphan wells in direct relation to maybe where there's a lot of pumping, on kind of the more finite scale, rather than thinking about it on this potentially large picture, which might better address that question.
I mean, oh my gosh, so you're bringing up some issues that are of incredible importance to, I think, every person who might be attending. And that is the whole issue of fluid flow in reservoirs and across all the different lithologies. So that brings to mind so many additional ideas and thoughts. I mean, yes, there's wellbore integrity in the producing formation that could potentially leak and go into the borehole, but then let's think about what else is potentially happening, especially if we're in an area that has active horizontal drilling in different zones, and you have hydraulic fracturing, and then you have fracture networks that develop, and then you have fluid migration pathways. What exactly is happening? And then the using the tools we have when we look at migration pathways or what's happening during production or early on in the origin and migration of oil fluids, etc. Let's I mean, these models have so much potential for application across different purposes.
Totally agree.
Yeah. So I mean, I was thinking, what kinds of work do you envision doing in the future for like simulation of fluid flow?
I'm not sure that we have anything, necessarily directly in the pipeline, but I think it is something that we're actively thinking about, maybe incorporating into future projects. I mean, I think Nick, Carl, and our expertise is not necessarily in, this direct groundwater flow modeling, but we have some incredible scientists at the USGS that do just that. So, if the questions drive us that way, and that seems like where the interest is, we can definitely start to think about that a lot more, Susan.
Yeah. I think that's quite interesting, and I think the potential for really teasing out cause and effect, but also having a better understanding of what happens over time is really fascinating, because what we're seeing is the potential for stimulating and accelerating fluid flow.
Yeah, and I think that's kind of this, the major question for us with the orphan wells in particular is, just it's the age component, right? I think we like thinking about orphan wells because, it's not necessarily every well, but other wells may become orphan in the future. So it's, this potential end of life cycle for kind of many of these, and just kind of the sheer age of these, over time, and what that could be or could not be doing to groundwater over that time period. It's an interesting kind of thought exercise for sure.
Right. Jerry McCaskill has a great question. Is there a USGS map of pre-drilling aquifer conditions? Oil springs, gas seep, salt plains, etc.
I am not aware, but that being said, we have been around as an agency for a long time, and we have a lot of cool stuff in the record books. So there may be old water quality data that could be used to put together an old a historical water quality map. I would also like to point out that our colleagues at NETL are using USGS maps from the 1930s, 40s, and 50s to build maps of I guess orphan wells to be documented again. So I can see that there's a possibility that our old mapping products could be used to create that kind of thing.
it would definitely be, I think, a pretty incredible exercise to try to get that together, but that would be quite a useful one.
Oh yeah, yeah, definitely. Okay, so here's kind of a thought piece. We presently do plug and abandon, which might be better described as cut and run. Well, anyway, that's a thought. Present P&A methods make sites look good and blocking the wellbore, but are we just applying a temporary plaster in the wellbore rather than fixing the problem and protecting the reservoir? Should we not be looking at better ways to protect groundwater? What would those be?
So,
Go ahead.
go
Carl.
ahead. Okay. I was going to say, we are very interested in developing a better understanding of what makes a good plug and why plugs fail. I think that we're starting to see a lot of questions coming from policymakers about, like, what do we know about the integrity of plugs over time, and that could be a place where our research goes in the future. So I know that that's sort of adjacent to your question, but we're getting questions now that are along the lines of, like, well, this well was plugged in 1980. We thought it was a good plug, but now there's problems. Like, what happened?
Yeah, and there's been a standing question right now is how long does a well plug last in a well, and nobody really knows. And also, when we look at the quality of well plugs, you know, they've improved significantly. So wells being plugged today are a much higher plug job being done in a much better way than they were 50 years ago. And so another kind of concern is what happens to all the wells that were plugged in the 50s, 60s, and 70s is what we're seeing out in West Texas with some of these wells starting to fail.
Or
You know,
1910s.
Sure. You know, and so are we going to have a whole nother slew of orphan wells that we thought were plugged that end up being failed plugs down the road? And that's something we don't like to think about a lot, but it is something we need to be aware of.
That's really interesting. And there have been a number of different approaches taken with the idea of, like, say, using different types of clays, et cetera, just pumping those down and using sort of natural barriers that in theory would be working with nature. But and we've had a number of those presentations at our Orphan Wells conferences. So I say, hey, let's stay tuned for all the research that's going on. I would like to encourage everyone to look at the answered questions. Go to the Q&A and click on answered, because there are some very valuable answers and links there, very valuable data sharing. And we're about out of time. There's no way we could get to all the questions. So I just want to thank everybody for your enthusiasm, and to remind everyone that you will be getting an email with a link to the recording. And I just, again, want to thank our presenters, Nick and Josh and Carl, for being here and sharing and being so open with answering all kinds of questions. So any final thoughts?
Just happy to be here, and really excited that everyone was engaged and interested in this topic. And I think as Carl and Nick have said, I would just love to reiterate that we're doing this work to help you guys, and if you guys have thoughts, questions, ways we can improve the products, ideas that you think are interesting, we're always happy to hear them. And I think our contact info has been shared, so please reach out. We're really happy to hear the feedback, because I think in our eyes we do this for you guys. So
thank you, everyone, and Nick and Carl.
And thank you, Susan.
Thanks, everyone.
Thank you. Well, until the next time. And this was wonderful. Thanks for all the heart hands and hearts and so icons, celebratory icons. Thank you.